Real gases are non-ideal gases. They do not adhere to the ideal gas law because their particles have interactions. The product of pressure and volume is no longer a constant at high pressure. For example, the PV of helium increases with pressure. In contrast, the PV of methane and ammonia decrease with pressure. First, an ideal gas consists of point particles. In contrast, real gas particles have a finite size. When they get close enough to interact, their electron clouds repel each other strongly due to Pauli exclusion principle. That repulsion acts as if the molecules had a solid boundary. The particles occupy space means the free volume available for motion is less than the apparent volume. So, we replace V by V minus NB, where B is the excluded volume per mole. Second, ideal gas law assumes particles do not attract each other. In reality, gas particles attract each other with van der Waals forces. The strength of attraction depends on the type of particles and their distance. When a particle collides with the container wall, nearby particles pull it backward, reducing the speed of collision. So, the observed pressure is less than it would be if there were no attractions. The force pulling a particle back is proportional to the number of nearby particles. The number of neighboring particles near the particle is proportional to the particle concentration. Meanwhile, the number of particles contributing to the total pressure is also proportional to the particle concentration. So, the total reduction in pressure is proportional to the particle concentration squared. Putting both corrections together gives van der Waals equation. With van der Waals equation, the microscopic properties, i.e., the particle size and intermolecular forces, can be derived from macroscopic properties, i.e., pressure and volume. For example, helium is nonpolar, so it has very weak London dispersion forces. At very high pressure, helium atoms are close together, so the repulsion becomes significant, causing the observed pressure to be higher than predicted by ideal gas law. Ammonia is polar, so it has strong Keesom interaction. At high pressure, ammonia molecules are close together, so the attraction becomes significant, causing the observed pressure to be lower than predicted by ideal gas law. The calculated A and B values from van der Waals equation are in accordance with these microscopic facts. The essential character of the isotherms of the van der Waals equation on a PV plane is that they come in three forms. At higher temperatures, the isotherm's slope is negative everywhere. It satisfies the stability criterion, like ideal gas law. At some critical temperature, the slope is negative everywhere except at a single inflection point. The critical point, where both the slope and curvature are zero. At lower temperatures, all isotherms have 2 points with zero slope. Between the 2 points, the stability condition is violated. Suppose the system is in equilibrium with its surroundings with same pressure. If the isotherm's slope is negative, a small increase in volume reduces the pressure. The pressure difference between the system and the surroundings produces a restoring tendency that opposes the fluctuation, negative feedback, so the system returns toward equilibrium. In contrast, if the isotherm's slope is positive, a small fluctuation that increases volume increases pressure, which can reinforce the fluctuation, positive feedback, and drive the system away from the equilibrium. The unstable region is the genesis of the phase change. There is a range of volume, for which no observable state exists. The state of low volume is condensed phase, and that of high volume is its vapor. The state above the critical temperature and pressure is supercritical fluid.